Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. So today we have Dominique Perrault-Jonca coming across the frozen lake all the way. And Dominique has gone to McGill before he came to UW. He recently won the Bernstein Prize from Statistics Department, and he'll tell us today all about manifold preservation and metric learning.
Thank you, Misha. So I'd first like to thank Misha and Hoyt for organizing this talk and for inviting me here. So I'm going to talk today about metric learning and preserving the intrinsic geometry. And this is joint work with Marina Mela, Professor Mela at the University of Washington, who's my advisor for my PhD right now. So a brief overview. I'll give some background on the problem. I'll cover some differential geometry theory just to get you acquainted with the framework, and because I think it's good to be reminded of it, even if you're somewhat familiar with differential geometry. I'll discuss the discretized problem and the algorithm, and then I'm going to show some example and application. I'll give a brief summary and future research, and maybe I'll get to the consistency of the push-forward metric, but maybe not. I'm not sure that's the most important thing to do. So the problem we're trying to tackle here is the curse of dimensionality. There's currently an abundance of large data sets that are high dimensional. And this leads to some problem in terms of interpretation, in terms of computation, and in terms of analysis. And so the idea is to try to reduce the dimension of the data set. And underlying this idea is to try to find some low dimensional representation of this data, but that will preserve all the important information, or at least most of it. So that's kind of our goal today. And so I'll start by giving you a toy example that's kind of going to follow us through the talk. And so it's worth going over what this example is. So effectively, what we're going to be looking at are images. So it's going to be faces, gray faces, 64 by 64 pixels, and we're going to have about 700 of those images. So we have a fairly high dimensional data set. I mean, it's still small by today's standard, but I think it captures the idea. But this data set has some very interesting attribute, which is that it represents one specific face that's only moving right to left and up and down. And so in this data set, what we have implicitly is only 2 degrees of freedom. And so we're going to try to leverage this attribute of the data set to help us in our analysis.
I understand. So it's all images of the same face taken from different points of view?
Let me show you the data set itself. So this is actually one embedding of this data set. Every single ellipse on here is one of the faces, and I'm showing you a subset of those faces. So it's always this particular face that's being rotated one way or the other, or that's tilted up or down. So
actually the difference is just the point of view of the camera.
Exactly.
With respect
Yeah. It's either the head or the camera, depending on how you want to see it. And so we have 2 degrees of freedom, even though in terms of representation, every image is 64 by 64. Right? And so the idea is to effectively find an embedding like this one of the data and try to use this embedding to do analysis or to do some interpretation. So in this case, it's fairly easy. We found that one dimension represents the angle of the head in terms of left and right, and the other dimension represents the angle of the head from up and down. So far so good. And so there's a lot of embedding that exists. I'm showing you a subset of here, and they all do various things. The question then is, which one makes the most sense? So the underlying idea for dimensionality reduction is what I said before, is to assume that the data lies on a low-dimensional smooth manifold that lives in a high-dimensional space. So the high-dimensional space is the space of the data, and the low-dimensional manifold is the data set, or what the data set would look like if we had every point. And the idea is to recover this. Now, there exist standard techniques such as PCA, principal component analysis, that are going to make an assumption that the manifold is a linear space. And so they're just going to project on a linear space. But in practice, this is often violated. The data set will curve and twirl and do many things in the high-dimensional space. And this has led to nonlinear dimensionality reduction, which means trying to find what's the curve of the data set in the high-dimensional space and try to take that into account when you project it into the low-dimensional space. And so there exists already many algorithms to do that. I've already showed 3 of them, but this is, I think, a list that certainly is not exhaustive, but covers some of the important ideas that have been developed in this field. So local linear embedding is a fairly, well, they all work with the same idea, which is that you use local information and you try to propagate it in such a way as to recover the full manifold. And so local linear embedding, what it does effectively, it tries to express every point as a linear combination of its neighbors. And it's going to use that to then recover a lower dimensional representation that preserves this local weighted average. The Laplacian Eigenmap and the diffusion map work slightly differently in that they, what they do is they define a random walk on the set of points and use that diffusion process, so to speak, to find an embedding. So it does an eigendecomposition of the random walk or the diffusion process and use this eigendecomposition as the embedding. And then you're going to have other algorithm like linear tangent space alignment that is based on the idea of doing local PCA and then patching those PCA together into one embedding, or Isomap, which tries to preserve a very specific geometrical object, which is the geodesics. So distances on the manifold is what you're trying to preserve when you do Isomap. But there are known problems with these methods. Often they will fail to recover the geometry, and there exists no formal framework to recompare them. And I showed you a few, but there really is a very, very long list of methods, and it's not clear when you start which one makes sense to use and why. And so to answer those 2 problems, what we first have to do is actually define what it means to recover a low-dimensional manifold. For example, if I use a very simple manifold, a classic example, which is a Swiss roll, which has a hole in the middle of it, we have 2 potential embedding. This would be the Isomap, and this would be the linear tangent space alignment. And it's not clear from this image which one's correct. We kind of know this is probably wrong in some sense, but we don't have a framework to say whether this is correct or not. So underlying all of this is we're assuming that recovering the geometry is an important goal. And we know that this is possible, that if there is a manifold, we have theoretical guarantees that there exists at least an embedding of the data. So if we know we have a manifold of dimension d, we have guaranteed there exists an embedding of this object into a lower dimensional space, which is of dimension 2d. So you can, any manifold of dimension d, you can embed in R2d, effectively. And so we know there is a way. We know that there's an option for us. But rather than try to do what a lot of manifolds are doing, manifold embedding methods are doing, which is to try to find the proper embedding that preserves what they care the most about, we're going to try to go around this and say, well, is there a way to correct an embedding? Is there a way to say, well, I've distorted my space and I'm going to recover the proper metric even though my embedding is wrong? And this is called recovering the Riemannian metric. So to formalize things a little bit, when I'm talking about an embedding, I mean that I have some manifold and I'm finding a map from that manifold to a new manifold, and that means it's going to send every point from one manifold to every point in the other manifold, or to the image of the map. And it also has the meaning that if it's an embedding, it's differentiable, which means it also maps point in the tangent space of the original manifold to points in the tangent space of the manifold in which you're embedding, which in our case is going to be Euclidean space. And this is important because geometry is defined in terms of the Riemannian metric, which is just a inner product here that is defined on the tangent space. And so what that means is, if you know the inner product on the tangent space for a given geometry, then you know everything you care about. And the idea then for us will be to say, how do I recover what the inner product should be in the embedding to correspond to the original geometry? So to drive the point of what it means to have the Riemannian metric, it means that you can do inner product, but then that means I can do all the usual geometry. I can compute angles between vectors in the tangent space, which means if I have a line, two lines crossing each other, I can try to say, well, at what angle are they crossing each other? It also means I can compute the length of a line on the manifold, and it means I can compute the a volume of a subset of the manifold, or the full manifold. And so effectively, I have the volume element, which is quite important if you're trying to do, say, define a Hilbert space on your manifold, which is kind of key to do kernels or Gaussian process. So if you have a space of functions on your manifold, and you want to use those functions to do any form of regression or classification, well, what you actually need is a volume element. So this is where we start thinking a little more in terms of learning and statistics, and less in terms of geometry. But the key idea is that all of this is encoded in the Riemannian metric. Okay, so before we go forward, it's still worth defining one more thing, which is an isometry. If I have an embedding or a map from one manifold to the other, we say that the manifold are isometric if this map satisfies the simple condition that under the Jacobian of the map, the inner product in both space is equal. And so all we're saying here is that if you do know your inner product, then you've defined your geometry, but then the point of having an isometric embedding is just a question of preserving the inner product. That means that given an embedding, I can try to define what's called a push forward, which is to say, if I have the original manifold that I'm mapping into a new space, the new space has its own inner product. How do I correct the inner product so that it's equal to the original one? And this is effectively how you do this. It's by looking at the inverse of the Jacobian, or the pseudo-inverse, depending whether this is full rank, so that the inner product in the embedded space is now equal to the inner product in the original space. Yeah?
Can you give an example of an isometric map?
I mean, the identity map would be an isometric map. You could unfold the I don't know if that's what you were thinking of, but if you have the Swiss roll, you could just unroll it, and it would preserve all the geometry. It wouldn't have the same curvature, but that's because the curvature you're losing is the extrinsic curvature rather than intrinsic curvature. So that would be an example. But in effect, what I'm doing will be to define isometries, right? Instead of trying to find the map that creates the isometry, I work the other way around by saying, given a map, how do I turn it into an isometry? What Riemannian metric must have existed in the manifold in which I'm mapping to, so that now it's isometric?
Why does that apply to the let's say images, like collection of images?
Because if you're mapping into Euclidean space, right, two-dimensional Euclidean space, the Euclidean space has its own metric, which is the identity metric, right? And that metric no longer preserves the inner product in the embedding. And the idea is to say what should have been the metric in Euclidean space so that now it preserves the inner product, right? So when you're doing an embedding, there's the question of, does the manifold in which you're embedding already has a metric? And usually it's an implicit metric. And Euclidean space is the identity one. But I could have defined Euclidean space with a different metric so that when I mapped, it turned out to be an isometric embedding, right? So there's kind of the subset, or there's the topology of the object into which you're mapping, and then there's geometry, which is the metric.
So eventually, following this line, it means that when you do this embedding, actually for every point you embed, you'll have both the point which represents it and the kind of the tangent vector which represent the metric.
So it's going to be it's not going to be a vector, it's going to be a quadratic form that's going to define the inner product at that point.
So actually the dimension that you map to is higher than the dimension of the Euclidean dimension of the space, because you also have this quadratic form.
Right, so in terms of memory, yes, you're keeping around d squared. So if you're mapping in dimension d, you also have to keep around this quadratic form, which is going to be d squared. And the hope is that d is so much smaller than the original space that you're still doing a considerable dimensionality reduction. Yeah, that's the underlying idea.
Is preservation in tangent space required for volume preservation always? Because it seems like the practical application would be like the practical consideration is that as long as volumes are preserved, then we get good properties with the kernel level and so on. But do you need?
I don't think you do. No, I think. It's an interesting question that I'm actually wondering about, because you're right, you can define your Hilbert space just in terms of your volume. But as it turns out, I think it's actually simpler to just get both at the same time. It's true that you don't necessarily need your tangent space. It can be useful in some cases, and I know examples where it's useful. But it turns out that it's actually very easy to obtain the metric, or to obtain the object that contains it. So, okay, the idea is, how am I going to find this, what's called a push-forward metric, which is the corrected metric for the embedding? And the idea is to use the Laplace-Beltrami operator that's defined in terms of the metric. And it has some very nice property, one of which that comes out of this work is that it contains all the geometry of the object, and at the same time it's coordinate-free. It can be expressed in local coordinates, but it is coordinate-free, which means that if you've computed the Laplacian for the object, any way you represent the object, the Laplacian stays the same. And it contains all the important geometry. And so what happens is, if you want to recover the metric given the Laplacian, all you need to do is apply the Laplacian to a product of coordinates. And that will tell you what is the metric, well, actually the inverse of the metric for those two coordinates. And so you compute it for all pairs of your embedding or your manifold, and it'll give you the full quadratic, or the full inverse of the quadratic form. Which means that if you have an embedding, the same trick applies. And that, by definition, gives you, actually you still need to prove it, but this will give you the push-forward metric. And so the point is, if you do know the Laplacian, you know how to correct your space. And so in practical terms, and I think I've kind of explained that already, but given a sample of my manifold, sample according to some density, and an embedding of that manifold into Euclidean space or some space, I can recover the full geometry by simply applying this trick locally. And so I'll recover at every point a quadratic form that expresses the inner product at that point. It gives me the volume element or any other geometrical object I'm interested in. And so the idea is to get an approximation of the Laplacian on the discrete space that will then give me all the geometry I'm interested in. And the idea is that this already exists. It's a common trick that probably some of you, or most of you, are familiar with, which is to construct a graph Laplacian by applying a kernel between every pair of points. Here I'm using the classic Gaussian kernel, and then defining this thing here, which is just a random walk on the graph Laplacian, or on the graph. And this is called a normalized graph Laplacian. And if you take the limit as you let the bandwidth goes to 0, this is known to converge to the Laplace-Beltrami operator on the manifold. Now here I'm assuming actually that the sampling density is constant. If it isn't, there's a trick to renormalize the graph so that the graph Laplacian now converges to the
How would you know that the density is?
sorry, what?
How would you tell if the sampling density is based on the collection of points that you have?
Well, so that's kind of the idea of renormalizing the graph, which is that you can renormalize it without knowing what it is, and it will give you the same object in the limit. So you don't actually need to know whether it is uniform or not. And so I'm showing you it's just to avoid being overly complex in this slide, but there's a trick that guarantees that you'll have the right Laplacian. Okay. And so this means that for us to recover the Riemannian metric, it's a simple case of obtaining the graph Laplacian, finding an embedding, and then applying the Laplacian to the coordinates of this embedding. And this will give us the geometry. So we're going to end up with an embedding of every point with a quadratic form at every point. And this is what it looks like. So I'm taking this object, which I call the hourglass, and then I'm using I believe, the diffusion map or the eigenmap to embed this object, which kind of changes the form. It makes this part less curved and this part a little flatter. And so what I get effectively is this object. So every line here is expressing the graph. It's just telling you what your neighbors are. So you still have a notion of topology. And every ellipse represents a quadratic form at that point. And so if an ellipse in that space is circular, that means that locally the embedding was isometric. If the ellipse is distorted, it's telling you by how much you've distorted your geometry at that point. And so we're finding that in the middle, this is fairly isometric, but as I move towards the edge of the hourglass, I'm starting to see that the metric is being effectively pooled, which means that every unit of point is worth more. So that means it's being compressed. So what you're seeing is actually the opposite of what's happening. The longer the metric becomes, the more every point is worth, so it means it's being compressed compared to the original metric. And here actually at the edge we're starting to see some artifact because it's starting to be difficult for the curvature. So when you're defining the Laplacian, you're starting to see points that shouldn't be observed because it's not sampled densely enough. And so there's kind of the implicit idea that this works well provided that the manifold is smooth and doesn't curves too fast. But if it does, you need more sample points. Okay, so what does it mean in terms of the original data set I presented to you guys? Well, it means that if I look at the three embedding I first showed, we get a clear idea of what's happening. So if I use the isomap, I'm seeing that effectively the embedding is fairly close to isometric. It's not quite correct. It's being stretched. Well, it's actually being stretched in this direction and it's being compressed in that direction. But otherwise, it seems like it's preserving the geometry of the data set. Well, if I'm using linear tangent space alignment, I'm seeing quite a fair bit of distortion at the edges here. And finally, the Laplacian Eigenmap, which is still one of my favorite, has a lot of distortion in it. And so this now allows us to make actual explicit statement about what's happening in the embedding.
So actually the distortion is the variance in the shape of the quadratic form. So if the quadratic form is distorted but equivalently, as we see in Isometric, it is distorted, but it's distorted in the same fashion in all points. That means that actually it's...
Right, and actually that's an important point because now if it's only being linearly distorted in different dimension, it's easy to use one point and then rescale everything, which I'll do in a second.
By LTSA, local tangent. This is a local tangent space alignment.
Yep.
So because LTSA is supposed to be isometric, why the result is so different from isometric?
I mean, that's kind of what I'm trying to, I'm using their code, but that's what I'm trying to show is that actually we think we're doing a good job, even the algorithm that are trying to be isometric.
So result for Gaussian Eigenmap.
So for this
approach by David Donahoe.
This one?
No, Gaussian Eigenmap.
Oh, Haitian, okay, yeah.
So do you have a result for that one?
I haven't tried it. I mean, to be able to define an algorithm that will always isometrically embed your data for any manifold is equivalent to solving Nash's theorem. And so I take for granted that we don't have an algorithm that will be isometric. There exist theorems that you can show it's isometric if you're in L2. And so if you have an infinite space, it's easier to construct something. But if you're trying to embed an Euclidean space of low dimension, it's very hard. You could use Nash's embedding theorem that guarantees isometry, but it means twirling around dimensions. And so numerically, it's very, very unstable. And
analysis, David Donahoe proposed Gaussian Eigenmap. His motivation is to be isometric because from his analysis, LLE is not isometric. Isomap can be isometric, but isomap has a problem if there is a hole in the surface and then it will fail. And David Donahoe tried to fix. David Donahoe proposed his approach to fix the problem.
Right.
And in his analysis, he used the non-space of Gaussian for embedding. From the differential geometry, the non-space of Gaussian can keep the distance, geodesic distance.
Mm-hmm. So I'm not sure I'm going to fully address your question, but I think the main point that comes out of this is assuming you do have an algorithm that will always give you an isometric embedding that preserves everything you want. Most likely you're giving yourself too much trouble. Because the idea is, it's true this embedding is no longer isometric, but I do know by how much. That means I can still do computation in this embedding without having to worry by the fact that if I ignore the quadratic form, it's not isometric. Which means I can, instead of trying to find the best embedding, I can find a quick embedding and then correct it. So the idea is that it can save you in time. So Isomap is already known to be a computationally intensive approach to the problem. And so you could try to define something as simple as like random projection that are super fast. As long as you have enough of them, you're defining an embedding, and then you can correct it. And so that's kind of where I'm heading to. I'm not trying to say there doesn't exist the perfect algorithm. Maybe there is. I don't think it's easy to find one that will work all the time. But I'm trying to say maybe we shouldn't try to find one because we can do better. We can, given an embedding, we now know how to do all the geometric operation you may care to do. And so it's about finding quick and efficient algorithm and then correcting them, I think, is the best way I can approach a problem. I don't know if that's what you feel. Does that answer your question?
You may check David Donahoe's paper because he put some theories about how his approach can keep the geodesic distance by using the non-space of Gaussian for embedding. Actually, perhaps at that time, David Donahoe didn't realize his approach actually is perhaps just another version of the local time space alignment. Both are related by Gaussian. But so far, the people analyze that. So if Gaussian Eigenmap can be isometric, then suppose LTSA is also can be isometric. We will discuss offline.
Yeah, I think we should cover that offline. But to make a final point, and I'll continue after that, we can talk, is the geodesic is not the thing I'm the most interested about. The volume element, as Misha pointed out, may be the only thing I actually care about. Okay, so LTSA, which seems to work initially, but actually turns out to be slightly distorted. But this can be corrected, as you pointed out, by just essentially, if the distortion is along 2 dimensions, it's easy to use the metric to then rescale everything. And so this is what I did here. I have something that looks isometric but is actually slightly distorted. And then I use 1 point to locally transform everything. And then it turns out that pretty much everywhere is now isometric. But if I have something that's distorting too much, like the naive isomap, then I can only apply this locally. So if I try to use 1 point here to correct the space, I will be able to correct around that point, but the rest of the space remains distorted. That's fairly intuitive. But this is where I think it becomes slightly more interesting, which is to say, well, actually, I don't need to worry about the embedding. If I know the metric for a given embedding, I can do computation. And so what I do is I consider an original manifold, and I have a line around it, and I'm trying to compute the geodesic. I can do it, say, in the isomap that's supposed to preserve the geodesic, or into any other space. And so if I found the distance in the embedding, I'm getting wildly different results. If I'm using the shortest path in the graph defined by the embedding, I get very different result. But if I correct the distance here by the metric, I'm effectively getting the same thing. Now, it's not perfect, but I'm seeing that all the embedding now has the same geometry. I can compute the same geodesic, irrespective of which embedding I'm taking. And I can do this for volumes.
So this relies on the fact that the kernel that you use to compute, to approximate the Laplacian is the right, well, it's the approximation is good to the metrics of interest.
Yeah.
On the other hand.
So yeah, the idea is that kernel, the Laplacian that I'm using to define the metric, is kind of key because it contains all the geometry. Now, it doesn't mean if there are errors, it might no longer be the original geometry. It's an approximation of it. But in and of itself, it will always compute the same geometry. Right? And that's actually a very important point because it might turn out that the original geometry is not what you care about. But that just means you have to find a different Laplacian. And that object will give you the same geometry, irrespective of what embedding you have. So I can play the same trick with volume element. And effectively, I'm finding the same thing. More errors, in part because I'm using a coarser discretization of the space. But effectively, I cannot even compute the volume element for some embeddings because it doesn't always make sense. But if I use the correction, I'm pretty much all in the same ballpark. All right, so that kind of ends the geometry part. And now I'm trying to move and explain what it means in terms of learning. And so now that I've established effectively that the Laplacian contains all the geometry, the idea is how can you use that to your advantage? Well, it's known that in Euclidean space, this operator, which is the usual Laplace operator, if you look at this SPDE, it defines a special Gaussian process. So I'm assuming that this here is Gaussian white noise. And you can show that the covariance matrix of this object, well, first this is a linear operator. That means that U is a linear combination of the Gaussian white noise. And so it will be Gaussian. And then the question is, what's its covariance matrix? And you can show that it's a Matern Gaussian process. And so the idea is this operator effectively defines what a Matern Gaussian process is. And then you can use that to advantage by saying, actually, I can replace the Laplacian by the Laplacian of my manifold, and now I've been able to define a Matern Gaussian process on the manifold. And I can use that covariance matrix now to do semi-supervised learning, whereby I know the value of a function at certain points, and I'm trying to predict it over the rest of the manifold. This one.
How is the Matern Gaussian process different than regular?
So Matern refers to the covariance matrix, or the covariance function. It just says So a classic one is the square root exponential covariance function. But it has the disadvantage that it's infinitely differentiable. So it's a very smooth process. And the return is one whereby you can actually control how smooth it is. So the alpha parameter here determines how many derivative your Gaussian process will have.
Okay.
Yeah. And so it gives you much more control in terms of when you're trying to do prediction, how smooth is your kernel or your Gaussian process, depending on how you want to think about it. So given the Laplacian, now I can define a return process, and I can define a covariance matrix. Actually, this should have been with respect to the manifold. But I can then do learning, predict what the value of a function should be at other points, given what I know, based on the geometry. So implicitly, I'm learning the geometry of the manifold, and I'm using that to propagate the information. And so you can do that. You can think of this also just as being a kernel or a kernel regularizer for your regression or for your classification. What's actually interesting is that because now we have the metric, you can also define the precision matrix not only on the points, but through the embedded space. That means that instead of just learning on the points, I can learn around the point. So if I have a new point that arrives and I know where to embed it, I will immediately know what the value at that point should be, or what the class at that point should be. And so this is a slight departure from traditional semi-supervised learning in that I'm actually doing inductive learning, but in the embedded space. So here's an example of how this works out. So I'm using the three embeddings that we've followed through for the faces data set. And what I'm doing is I'm embedding the points for all embedding of interest. And then I'm applying a return kernel with respect to the embedding space. So I'm actually assuming that this is the correct geometry and applying a Gaussian a return kernel to then predict what the value of the function should be. So what I'm doing effectively is I'm keeping track of about a little less than a quarter of the values of the head's position, and I'm using it to predict what the value should be elsewhere, right? And so if I'm using the embedding space, I'm getting quite a fair bit of error. But if I'm actually using the intrinsic geometry, I'm doing a lot better, right? And so that's kind of the idea, which is to say that the original geometry of the data for this particular data set turns out to be the right way to propagate the information.
Color code? Does it mean what?
This is how wrong a particular point is, right? Because these are angles. It goes from 0 to 180. And that's telling you compared to what the actual value of the point should be.
So these are the points. So you said, I don't remember how many points that
There's about 700.
700, part of it you used as your training sample and part of it. So these are just the test points, right?
I'm actually showing you both the test and the train set. So the tests are about, I probably should remove them. But they'll be, I'm using about a quarter of them, and they'll all effectively be right. You're going to have the right value at those points. So they're not contributing to the error.
So for example, in the Laplacian Eigenmaps, is the reason, so it seems to not be performing well.
Mm-hmm, mm-hmm.
Is it because of kind of the sparsity on the right side? So what is...
I just think that what it's doing, it's not recovering the right geometry. And so it's actually, well, first the information doesn't propagate, like the kernel is a stationary kernel. And so effectively, by stretching the space, it's not propagating the information the right way. But you're right that the sparsity here is a problem. And what's happening is effectively you're doing regression on part of the space that is now part of the ambient space, because you'd assume that there's no manifold here. But because your kernel is defined for the whole of Euclidean space, you are not using the space intelligently. Well, if you define it here, you're only defining it on the space you know. Right? So this is actually not inductive. This is now, the low one here is just transductive, which means I can only compute it on the points I know. Right? So I think it's both the fact that you're computing it with respect to the ambient space, but also because you're distorting too much of the space.
So if your final goal is for prediction, I don't see why it's important to recover geometry. So from when we use Laplacian for computation problems, so the leading eigenvectors actually, if you use the leading eigenvector of Laplacian for embedding, and the different classes will be well clustered. That's why Laplacian can be useful for classification.
Right.
And so you know the paper by Andrew Ng and Mike Jordan.
Mm-hmm.
They drew the picture. They have a paper about spectral clustering. So use the leading eigenvectors of Laplacian. If you use the leading eigenvector of Laplacian for embedding, and we can see different classes will be very well clustered, and then that will be easy for computation.
Yeah, and you raise a very important point, which is that I think I mentioned earlier. The original geometry is not necessarily the best geometry. I'm focusing on this because it's the first step, saying, well, first, can I recover it? But second, what comes out of this is the fact that all the geometry is contained in the Laplacian. If you think a different geometry is more appropriate, you should focus on defining a Laplacian that is appropriate for that geometry. Now, what you say, you use the first few eigenvectors of the Laplacian for your embedding, and that helps with clustering. What you're doing implicitly is define a new geometry. So the map that uses the eigenvectors to embed are effectively this map for this particular data set. And this is now a different geometry. It turns out that here is the wrong geometry, but for clustering, it tends to be better. And so the question is, and it's actually one of my open problem of how can we use what we're trying to do to select what geometry we want, what Laplacian we want for this particular problem. And so I think this is what comes out of this. I'm focusing on recovering the geometry. But an offshot of this is that we now have a way to characterize geometry, and we should think about what kind of operation we want, which then leads to what kind of Laplacian we want.
Do you ever think about the underlying process that generated the data? Like when I look at this problem, to me it seems like it's natural to think about some kind of model that generates this data that represents different views of the same sculpture head. And essentially what you're trying to do is recovering the parameters of, well, not really parameters, but the settings of that model when it generated this data. So one of the settings of the model might be the rotation of the head degree. But there's also a lot of other things that you can vary about the model that would correspond to other dimensions of variability. So,
what about this?
How would this map to that view of the world?
So here I'm using a fairly straightforward vision of the sampling process. I'm assuming IID according to some distribution on a manifold. But you make a very interesting point that there might be a different process that's at play and is of interest. And I think the best answer to that is to say, well, can I get an idea of what operator is generating this? Hopefully a linear operator, like a translation operator in this case. And if you do that in the same way that this defines a Gaussian process, if you have a linear operator, you can define a different Gaussian process that is representing the transfer of information better, right? Actually, there's a paper on this by Skolkoff, I think 2008 paper, that says, well, if we look at, say, Kalman filter, which is actually a generative process more in line with what you're saying, you can turn this into a differential operator. This operator leads to a Gaussian process, which is also equivalent to a kernel. And so there's there's a kernel that's intrinsic to your process. And so what I'm using here, I'm using this operator because it's the simplest one to use if all I'm doing is try to kind of interpolate between points. But if I know that there's something generating the points, I'm going to use a different operator that tries to mimic what I think is a generator, and that will lead to a different regressor. I'll get a difference covariance matrix, and I'll be able to use that to effectively transfer the information. But hopefully this would be with respect to the Laplacian that represents the geometry, but it might be that it isn't. And if it isn't, that's when you start saying, well, if I want to do what you said, but I want to do it in a lower dimensional space, I have to be able to represent this operator with respect to the correct space. And then I can start computing the metric and what is the operator with respect to that metric. So I guess what I'm saying is your operator, so that it becomes geometry invariant, you may need to compute the metric explicitly. In this problem, I didn't go through the whole issue of saying what's the metric at every point, because I only used the Laplacian. But there are cases where the process might require you to find a coordinate chart, or a coordinate system which is an embedding, and then compute the metric there to express the correct operator. Maybe I'm telling you more than you really wanted to know, but yes, I think there's a natural way to think about what you're saying, which is in terms of what operator generated the process. Right, so I guess I've summarized a fair bit already, but the original idea of this work was to say, well, we know that the embedding algorithm failed in some sense at recovering the geometry of the manifold. And most of the solution have been about trying to find one algorithm that does better than the other ones. And instead what we try to say is, well, actually don't worry about finding the correct algorithm. Try to find how to correct it in a meaningful way by defining a metric that's faithful to the geometry, the intrinsic geometry of the data or the geometry of interest to you. This means that it frees you from having to use more complex algorithms. You can use simpler algorithms and then recover the geometry for that embedding. It also means we've kind of unified all the methods by saying actually they can be made equivalent through this object. And now we can say to what extent. So when I say they're equivalent, I mean only in the asymptotic limit. That means that there might be more bias or more variance for a specific embedding in the discrete case. And so we can start trying to say, well, how much does that matter in practice? And now we kind of have a tool to compare the various manifolds through the metric. And now it also means it gives us a kind of natural way to define Gaussian process or regularizers, by which I mean like L2 type regularizer, such as kernels, that are faithful to the intrinsic geometry or to your geometry of interest. And the only challenge we get out of this is that now we have, if we actually work in a coordinate chart, we have to carry around a quadratic form that's going to be of dimension D2, and it also adds some complexity to the implementation of any method. And so where I see this going, the question to me now is more about trying to say, maybe the intrinsic geometry is not the correct one. What I care about is a geometry that helps me the most with my problem. And can I put a prior on what type of geometry of interest and use the points then to find which one is the correct one to use here? And how do I define a Laplacian that's robust to noise or variability? And now this is kind of a tricky question, which is why people don't always like manifold learning, which is that the Laplacian or the embedding will be notoriously sensitive to noise. And I think there's some work being done in that respect, which is to try to think about what geometry you're trying to learn. So it's kind of related to this, but there's some very nice work by Stéphane Mallat that's trying to define a geometry with respect to groups by saying, well, what are the natural invariant in my space? And that gives you a much nicer embedding, much nicer geometry. And then I didn't discuss this, but I can show the consistency of this algorithm, but only for one embedding, that is the Laplacian Eigenmap. And so for me, it's a question of can I extend that to general embedding, and then try to think about, well, what are the bias of my method, and the variance. So I think that sums it up.
Questions? I have one actually. So
Typically, you would use this in the context of some supervised task where you are doing like things using GPs, you can be doing classification. So if you wanted to push back the supervision, basically the label dimension into the algorithm, how straightforward or not would it be? Given all the interest recently in the supervised metric learning or semi-supervised learning.
So the idea is that if I don't have a supervised context, I'll go unsupervised and I'll just assume that one geometry is more interesting than another, either by arguments or just because it's the one I have. If I do have a semi-supervised learning problem, that's where I'm thinking about, well, I can just do the unsupervised part and then use it afterwards to help me with my supervised, or I can try to define, a subset of geometries and then try to find the one that matched the best. And implicitly, that's what people are already doing. What I'm thinking of here is this here. So here I have a bandwidth, right? That's going to define my graph. That's going to help me define my Laplacian. Now, if you're in a semi-supervised learning, you're going to try to use cross-validation or any other method of model selection to find what is the optimal epsilon. And that is in itself defining a geometry. The geometry changes as you increase your bandwidth. It becomes less and less interesting at some point. But if it's too localized, it becomes a geometry where the points are disconnected. And so I think this is already being done in effect.
The bigger effect arises when you have the locality being influenced by the supervision.
But you can look at it in a different way. You could say, since this is all this process is unsupervised, so you can say one of the interesting things, you say you have data, you might use it for different purposes. You want to compress it. So you want to find a representation which will be useful for many tasks that you don't know in advance. Because if you know the task in advance, why go this way? As you say, I might go directly to find the representation that will be best for the task that I'm interested in. But if you have multiple tasks or even unknown tasks, this is where this kind of a representation becomes interesting.
But I think the question then is that can you have a sort of a midway where you would have the representation, but then the task could come in, and then sort of some sort of the Raman solution where you have it. You have part of the embedding, but then it could be corrected using the supervision of the task.
Where then you have to keep also the original data, but if you keep the original data, so what's the point of this?
Well, it depends what they're doing to it. If it's just compression, or if it's just compression, then sure, as long as your d² is less than the original.
And so finally, that really depends on the correlation between the task and the manifold structure.
Yeah.
But they are strongly related, probably.
Right. If it's not very related, you'll just move in the space of potential geometries you're learning. Implicitly here, as I said, you can rescale the graph to so that the sampling density doesn't matter. But if you don't rescale it, it does matter. And there's actually a parameter that lets you tweak that, right? And so you can let the sampling density affect your embedding. And it's kind of clearer than just simply changing your ball. You're saying, to what extent do I want the sampling density to affect the representation of my data? And I try to find with respect to a task or not. If I do it without respect to a task, then I say, well, maybe I know I'll be doing clustering, but I don't know what's the clustering yet. And so I'm going to let it be an effect, right?
Obviously we make certain assumptions here, right? We make the assumption that the task that will come will be expressed on the manifold and not on its embedding in the high-dimensional space. Because if assume that I have a classification task, if actually, to solve it, I need to understand the embedding of the manifold in the original space. Well, I just dumped this information when I did this low-dimensional embedding.
Are you implying that the ambient space of the original space is important? Is that what you mean? That the
No,
actual
when I say that
structure of the object?
We make in all this line of work, we make an assumption which I think is a reasonable assumption, that if I have low-dimensional data embedded in high-dimensional space, then for most tasks, we really care only on the low-dimensional data nature of the task, and we do not care about the high-dimensional. So think about your faces, right? If the task, eventually someone tells you that the task is I will pick a specific pixel and say whether the intensity on this pixel is higher or lower than a certain threshold. Well, this has nothing to do with a low-dimensional representation of the data. Well, and any such embedding that you'll find, even if it's the best embedding, will fail miserably on this test. So you make the underlying assumption that any reasonable test that you will asked to do with respect to this data will actually care about this low-dimensional information and not the high-dimensional.
So I think we just agreed. My question meant that the ambient space of the data is important, and that's what you're saying, effectively. It's a fundamental question of whether the full space has some important information to tell you.
You have to make the assumption that the tasks that you want to perform, the sufficient statistics for that task are the measurements in the intrinsic, the low-dimensional space. Yeah.
Which seems like a very reasonable assumption, but this is going back to what you say. Obviously, if once I compressed, okay, I lost something, and someone can challenge me exactly on this.
Well, again, the intuition is that can you then compress halfway in such a way that the rest of the compression could then be informed by the task?
Only if it's a lossless compression.
Right.
Well, so I think what's being made explicit here is which part you're losing, which is the extrinsic geometry, which is the ambient space, but you're preserving all of the intrinsic geometry. But it turns out that for high-dimensional data, it's often the case that the intrinsic space is actually washing off the information. Right? If you try to do supervised learning in the high-dimensional space, you can't repropagate your information because you have so many dimensions to move around that nothing gets propagated, or it all gets propagated uniformly. And so it tends to perform better. It might not be the right one, but we just don't have the tool to really express what's happening in high-dimensional space. And so I feel like it turns out that in many cases it's the best assumption we can make because it's so hard to deal with high dimension and what it means to propagate in high dimension, propagate information. What's the covariance that's natural for high-dimensional space?
So you were saying that you were doing some more work currently on comparing this to kernels directly?
Right.
To just plain GPs with Gaussian kernels, basically with the Gaussian kernels?
Right, so it's the same idea of like using this to define a GP and then compare it to people who are doing kernels but are using a Laplacian regularizer. Actually, Zhu and Belkin have just come out with a paper in AI Stat saying, well, they consider the higher order regularization of the Laplacian, and that defines a kernel. And this kernel is equivalent to the GP process if you remove this K, right? So it's really an equivalent approach, is what I'm saying. Was there more you wanted to know about this, or okay, yeah. I mean, this goes back to the Skolikov paper that I mentioned that says there's a link between Gaussian process, kernels, and differential operator. You can move between the three pretty much as you will, or a regularizer, yeah. So.
Thanks, Dominique.
Thank you.